Hello friends, and welcome to a lecture on operation research. Today we will study the Big M method in simplex method. This is Professor Arvind Prasad. Simplex method is a method to solve linear programming problems, and in that method there is a Big M method too. As we go through the lecture, we will understand what is Big M method and why do we use it. So let's take up a problem. We have a glass frame company which has 3 plants. A new management has taken over. Plant number 1 produces aluminum frames. Plant number 2 produces wooden frames. And plant number 3 produces glass. Well, it can assemble glass windows. That is, it can use the frames from plant number 1 and plant number 2 and make finished product, that is windows, by putting glass in those frames, but it is not doing so. Since there is some profitability issue after taking over, the management has decided to study the operations of the plant, and the results are on your table. It is found that plant number 1 has 4 hours of slack time per week. Plant number 2 has 12 hours of slack time per week, and plant number 3 has 18 hours of slack time per week. Now, what is slack time? Slack time is the number of hours that the employees are not working. Also, it has found that to produce one batch of aluminum frames in plant number 1, it requires 1 hour. To produce 1 hour of wooden frames in plant number 2, it requires 2 hours. And to produce one batch of aluminum frame windows in plant number 3, it requires 3 hours. And to produce one batch of wooden frame windows in plant number 3, it requires 2 hours. If we sell one batch of aluminum frame windows, it will fetch us rupees 3,000 as profit. And if we sell one batch of wooden frame windows, it will fetch us rupees 5,000 as profit. So this is the way we express the problem mathematically. Our decision variables are x1 and x2, where x1 is the total batches of aluminum frame windows produced, and x2 is the total batches of wooden frame windows produced. Keep in mind that aluminum frame produced from plant number 1 will ultimately go to plant number 3, where aluminum frame glass windows will be produced. The similar can be said for plant number 2, where wooden frames are produced. The objective function here is z is equal to 3x1 plus 5x2, where 3 stands for 3,000 and 5 stands for 5,000 rupees. The functional constraints that we have is the batches of aluminum frame windows is less than equal to 4, and the batches of wooden frame windows produced is less than equal to 6. And of course, the third constraint put to us is 3x1 plus 2x2 equal to 18. The management has decided that there should be no slackness in plant number 3. That is, plant number 3 workers should not have any time where they are slack or they have no work. So we have 3 multiplied by, that is 3 hours multiplied by the batches of aluminum frame windows, plus 2 multiplied by x2, which is the batches of wooden frame windows produced, and the total of that should be equal to 18. That is, the total work done by hours by workers in producing aluminum and glass frame windows should be equal to 18. So we have written our objective function once again in the left side. To solve the problem using simplex method, we have to introduce slack variables. The slack variables are introduced to convert inequalities like x1 less than equal to 4 and 2x2 less than equal to 12 to equalities. The third equation, 3x1 plus 2x2 is equal to 18, does not require any slack variable. Now what do we find? To solve any simplex problem, that is a linear programming problem using simplex method, you have to start with initialization. The initialization starts with taking the non-basic variables, that is x1 and x2, the decision variables, as 0. If we take it 0, we quickly find that 3x1 plus 2x2 is not equal to 18. The equation is not satisfied. Now, how do we overcome this mathematical impasse? We introduce an artificial variable known as x5 bar in the equation 3x1 plus 2x2 equal to 18. Remember, x5 bar is an artificial variable. It is not a slack variable. This technique is known as the artificial variable technique. Also, we introduce a penalty in the objective function if x5 is not equal to 0 in subsequent iterations. So we write the objective function as z minus 3x1 minus 5x2 minus m into x5 equal to 0, where m is a very big number. If x5 after the first iteration is any time greater than equal to 0 or in the final result is greater than 0, then we have to pay a heavy penalty. Hence, this method is known as the big M method. Now, the augmented form with introduction of artificial variable and M is written on your left side. This augmented form is rewritten by eliminating x5 in the objective function, and that is on your right side. Next, we note down the coefficients of variables and prepare the simplex table. From the simplex table, we can find that if we move in the direction of x1, the increase is going to be 3m times, and if we move in the direction of x2, the increase is going to be 2m times. So therefore, the increase in direction of x1 is higher. So x1 is the entering variable, and we find what is the increase in x1 in equation number 1 and equation number 3 by treating the other variables in the equation as basic variables, as non-basic variables. That is, in equation number 1 we treat now x3 as 0, and in equation number 3 we treat x5 as 0. So the rise that we are going to get in equation number 1 for x1 is going to be 4, and the rise in equation number 3 for x1 is going to be 6. We take least of these two rises. So that's going to be, we are going to box this equation, and since in this equation x3 was treated as the non-basic variable, therefore our exiting variable now will be x3. The entering non-basic variable is x1 and the exiting non-basic variable is x3. So entering x1, exiting x3. Now we perform row operations to ensure that the coefficients of x3 in this table now get transformed as coefficients of x1. So there we are. Now we can find that the coefficients, after doing those row operations, we have found that the coefficients of x1 now are that of x3 in the previous table. Again, here what do we find? that if we move in the direction of x2, the increase is going to be 2m times. We cannot move in the direction of x3 because here the increase will be minus 3m times. Therefore, we box the coefficients in x2, and now we have to find the increase in x2 by treating the other variables as non-basic variables. So we find that the increase in x2 in equation number 2 is 6 and in equation number 3 is 3. We take the least of these two increases, so we take equation number 3. Therefore, the entering variable now is going to be x2 and the exiting variable now is going to be x5 bar. Now we have to see that the coefficients of x5 bar are transformed to the coefficients of x2 by doing row operations. So we perform these row operations. Now we find here that the coefficients of x2 are equal to the coefficients of x5 bar in the previous table. Again, here we find that if we move in the direction of x3, the objective function goes up by 9/2 times for each unit increase in x3. So what do we do once again? Box the coefficients of x3, find the increase in x3, and the lowest of the ratio is 2. So we take equation number 2, and therefore the exiting variable now we get is x4. So the entering variable is x3 and the exiting variable is x4. Now we transform the coefficients of x4 to x3 by performing again row operations. And this is what we get finally now. Now as we can see that our objective function has got the maxima or reached the maxima. Why? Because the coefficients of x1, x2 and x3 are 0 and the coefficients of x4 and x5 are positive. If we move in the directions of x4 or x5 bar, we will decrease the objective functions. So 36 now is the maximum value of the objective function. This transforms to 36,000 rupees. And the solution of course is x1 is equal to 2, x3 is equal to 2 and x2 is equal to 6. Therefore, this tells us that the batches of aluminum frame windows to be produced in a week is going to be 2 and the batches of wooden frame windows to be produced per week is now going to be 6. Now this is your final solution. So that was all guys on using the big M method to solve a simplex table or a simplex table. You have to use the big M method when one of the functional constraints is an equality. One or more functional constraints are equalities. When they are equalities, you have to introduce an artificial variable. That was all guys. If you find this interesting, do subscribe my channel. Goodbye friends. Have a great day.